Dr.C.MARIYAL from Electronics Communication Engineering. Today I am going to discuss about semiconductor device manufacturing process and challenges. What are the opportunities in semiconductor devices manufacturing process? These are the content we are going to discuss in this presentation. First of all, before we enter into the semiconductor manufacturing process lecture, we have to discuss about the National Semiconductor Mission in India. There is ISM. The India Semiconductor Mission is a Government of India initiative aimed at establishing a complete semiconductor ecosystem in the country, covering chip design, fabrication, packaging, testing and research. The main objectives of this National Semiconductor Mission by India is to reduce India's dependence on imported semiconductor chips, encourage establishment of fabs, OSAT units and design centers, develop a skilled semiconductor workforce, support startups, research institutions and academia. In association with ISM, also Make in India Atmanirbhar Bharat, we have focused on the semiconductor manufacturing process. It mainly focused on strengthening domestic manufacturing capabilities and achieving self-reliance in critical technologies including semiconductors. The main focus areas for Make in India are indigenous manufacturing of electronic components, reduced import dependency, strengthening supply chains within India, job creations in high technology sectors. These are the main focus area of this Make in India Atmanirbhar Bharat. And first we are going to have the introduction of semiconductors. Before entering into the semiconductor introduction, we have the introduction about conductors and insulators. What is conductors and insulators? Conductors are materials that is have the capability of easily allowing a flow of electrons, and insulators is the opposite of conductors. It have the restrictions in the flow of electrons. So semiconductors are materials whose electrical conductivity lies between conductors and insulators. The common semiconductor materials are silicon, germanium, gallium. They are used to manufacture microprocessor, memory chips, sensors, power devices, etc. Modern semiconductor manufacturing requires nanometer level precision. It is a foundation for all modern electronic devices, and it is used in smartphones, computers, automotive and power electronics and medical devices. The examples for the semiconductors in the day-to-day life we are using as mobile processor like APL, A7 Bionic and Snapdragon chips are built using semiconductor process. And what is the importance of semiconductor manufacturing? Because the semiconductor is the backbone of digital technologies. It is used for enabling smaller, faster, more efficient electronic device, and mostly drive industries such as AI, IoT, communication, automotive and medical aerospaces requires this semiconductor manufacturing. And manufacturing complexity increases with each technology node. That is from 10 nanometer to 7 nanometer and 7 to 5. Now it will be in 5 to 3 nanometer. And it also enables miniaturization, that is called more transistor per chips, and it is used to have the performances improved by one and energy efficiency and speed also. And the drive global industries are computing, telecom and automation, then space. The nanometer scale complexity is between 5 nanometer to 3 nanometer and 2 nanometer nodes. And the real example for the 2 nanometer nodes are NVIDIA GPS manufacturing using TSMC 4nm mode, or they are trying to be in 2 nanometer mode. Next we are going to discuss about the raw materials for semiconductor manufacturing. Here mainly we are using the raw materials of silicon, the main material. Due to why we are choosing this silicon is because of the abundance and ideal electrical properties. Next, quartzite, because it is refined to produce electronic grade silicon. Next, high purity required 99.999, that is 99 or higher. So we are having these materials as the raw materials for semiconductor manufacturing process. And the semiconductor these are the steps. Next we are going to discuss about the process steps, semiconductor process step, and so the steps for semiconductor manufacturing process. The first one is wafer preparation, second oxidation, photolithography, it is called as patterning. The next one is etching, deposition, ion implementation or doping, chemical mechanical planarization, metallization, final inspection and testing, packaging. In this lecture we are going to discuss about about the manufacturing process steps in detail. First we are going to discuss about the first step, that is silicon wafer preparation. Here the silicon wafer preparation, we are in need of silicon, and the silicon will be purified in a furnace, And for this silicon wafer preparation, the following methods are be in a very useful manner. The first one is Swarovski crystal growth method. Produce ingots of monocrystalline silicon, ingot shaping, grinding, slicing and edge rounding, wafer polishing, and the next one is creating defect-free mirror-like surfaces. These are the methods which will be used in the silicon wafer preparation. The first one is purification of silicon in a furnace. And the purification of silicon in a furnace means the silicon wafer preparation is the first crucial step in semiconductor manufacturing. It transforms raw silicon into high quality wafers that can be used to fabricate high integrated circuits. And it started with purifying the silicon and typically extract from the sand. The silicon is melted in a high temperature furnace to remove impurities and create ultra pure silicon suitable for electronics. The next one, Swarovski crystal growth method. The purified silicon, from the first step, the result purified silicon is then processed using this method. A small seed crystal is dipped into molten silicon and slowly pulled out while rotating. This produces a large cylindrical ingot of monocrystalline silicon, which is essential for consistent electrical properties. This is the second step. And the third one is ingot shaping. Here, the ingot shaping is nothing but it undergoes a grinding to smooth its surface, a slicing into thin discs and edge rounding. These steps prepare the ingot for precise wafer fabrication and ensures mechanical stability during later process. The next one is wafer polishing. After the ingot shaping, we are moving to the wafer polishing. Here, the wafer polishing, after slicing, wafers are polished to create a defect-free mirror-like surface. This is critical because any surface imperfection can affect photolithography and the performance of the final semiconductor device. So, wafer polishing is the crucial step in the manufacturing process. This is the just silicon wafer manufacturing process. The first one is sand, that is refinement. From the sand, you have just purify the sand, just purify the silicon through the crystal growth, and then it will be given to the polishing. Then after polish, it will be cut down into slices, and from the slices, we are going to from the slice, we are going to divide the big slice into small slices. What is wafer fabrication? Next, we are going to see about what is wafer fabrication. Here, the process of converting a silicon into a functional integrated circuits. That is called as wafer fabrication. Here, we are going to discuss about the following process: lithography, etching, deposition, doping, and planarization. The first step is lithography. The lithography is the process where a pattern is transferred into the wafer using light exposure through mass. This defines the microscopic circuits and transistor layouts. The next step is etching. After lithography, etching removes the unwanted material from the wafer surface to create the desired patterns. It can be done via wet or dry etching. There are two different etching methods are there. The one is wet etching and the other one is dry etching. The third step is deposition. After the etching process, the thin layers of materials such as insulators or conductors are deposited on the wafer to build transistor layers and interconnections. And the fourth one is doping. Doping is nothing but introducing impurities, and doping introduces impurities into specific regions of the silicon to modify its electrical properties, creating a p-type or n-type semiconductor regions essential for transition operation. Doping is nothing but adding impurities is called doping. And the fifth step is planarization. Here the planarization is often done by CMP, that is chemical mechanical polishing. It smooths the wafer surface after multiple layers are deposited, ensuring flatness for subsequent photolithography steps. These steps are repeated multiple times, building the complex multi-layered structures that form modern integrated circuits with billions of transistors. This is the wafer. From the wafer, how the wafer will be packaged is shown here. From the wafer will be just formed as a single chip, then it will be formed as a packaged semiconductor devices. The next step in the manufacturing process is oxidation. The oxidation is nothing but formation of silicon oxide layer on the wafer surface. Formation of SiO2 layer on the wafer surface. Oxidation is a fundamental step in semiconductor manufacturing, where a thin layer of silicon dioxide is grown on the surface of the silicon wafer, performed in a high temperature furnace, that is 800 to 1200 degrees Celsius. It is occurs in a high temperature furnace, typically between these Celsius. The wafer is exposed to oxygen or steam, causing a controlled chemical reaction that forms the SiO2 layer. To form the SiO2 layer, we can have the high temperature furnace. Using the high temperature furnace, the wafer will be this wafer will be typically between 800 to 1200 degrees Celsius. It acts as an insulator, serve as a protective mask used in transistor gate oxide formation. And the purpose of this SiO2 layer is nothing but it has several crucial loads. First is insulator, protective mask, transistor gate oxide. The insulator it electrically isolates different regions of the silicon wafer, preventing unwanted current flow between components. And the next step, for the protective mask, during subsequent etching or doping steps, the oxide layer acts as a protective barrier to shields parts of the wafer from processing. And the next one is transistor gate oxide. Most importantly, it forms the gate oxide MOSFET transistors, which is critical for controlling the flow of current in the device. And here the oxide layer, when we are introducing this the SiO2 layer, the main purpose of the SiO2 layer is the quality and thickness of the oxide is directly affect the device performance and the reliability. So pressurized control during oxidation is essential. This is the silicon surface. When you are going to expose the silicon surface into high furnace 800 to 1200 degrees Celsius, and just above the silicon surface, the silicon dioxide layers will be formed. And the next step is photolithography, that is also called as pattern printing. Here the photolithography steps are given here. And the first step is just we are going to apply the photoresist, then you are going to align the mask, then you are going to expose the the fiber process to the UV, and next you are going to develop the pattern. Next you are going to just have the high furnace. We are going to have the name called hard bait. The UV lithography used for 7 nanometer and below. And TSMC, there is Taiwan Semiconductor manufacturing process, and Samsung are using this. And applications are enabling smartphone CPU architecture creations. And the photolithography is a critical step in semiconductor manufacturing, where intricate circuit patterns are transferred onto the silicon wafer. Here the first step is apply photoresist. A light sensitive chemical called photoresist is evenly coated onto the wafer surface. This layer will define where material is ordered or removed. The next one is align mask. A photomask containing the desired circuit pattern is preciously aligned over the wafer. This ensures accurate pattern replacement. Here the patterning is nothing, also called, the photolithography is also called the name called patterning. The third step is exposure using UV or EUV. Here the wafer is then exposed to ultraviolet or extreme ultraviolet light, which passes through the mask and changes the photoresist properties in the exposed area. Next, after the exposure to UV, we are going to develop the pattern. The wafer is developed then, so washing away either the exposed or unexposed photoresist depending on the type used, revealing the pattern on the wafer. The last step is hard bake. It is nothing but the process of solidifies the remaining photoresist to prepare the wafer for subsequent processing steps like etching or doping. The real world example for the photolithography are currently used for the manufacturing at 7 nanometers and below in companies like Taiwan Semiconductor Manufacturing and Samsung to produce highly advanced chips. The applications of this photolithography is essentially for creating the complex CPU architectures found in modern smartphones, the central processing unit architectures, allowing for high performance and energy efficiency in a very small footprint. This is the photolithography diagram, a picture. The photolithography that draws the circuits on the wafer through the line. The first, we are having the wafer. Then you are going to form the oxide film. From the SiO2 layer, you are going to produce this SiO2 layer to the photolithography. Next one is the photoresist. And how we are going to have the masking process are just in the picture, the Samsung Semiconductor. The picture is from Samsung Semiconductor. The next step is etching. The etching is just here. The etching have two types of etching. The first one is wet etching and dry etching. The etching is nothing but the crucial process in a semiconductor fabrication used to selectively remove material from the wafer surface, defining circuit patterns and structures. Just you are going to remove the material from the wafer surface is called etching. And here the etching is divided into two types, wet etching and dry etching. And wet etching is nothing but it involves using liquid chemical solution to dissolve unordered materials. The etch is nothing but just to remove material. So wet etching is nothing but you are going to have some liquid chemical solution to dissolve the unordered materials. Here it is relatively simple and cost effective method. However, the wet etching is less precise because the chemical attack the material isotropically, meaning in all directions. This can cause undercutting and limits its use for very fine flutures. The next one is dry etching. It is also called as plasma etching or reactive ion etching. It is called RIE. And dry etching uses ionized gas or plasma to remove material. In wet etching, we are using the chemical liquid. Here, we are going to use the ionized gas. This process is highly directional, allowing for more precise and anisotropic etching rather than the wet etching. This dry etching is widely used for fabricating nanoscale features due to its accuracy and ability to produce vertical sidewalls in edge structures. While wet etching is suitable for bulk material removal or larger features, dry etching is the preferred choice for advanced semiconductor device requiring fine nanoscale patterning. The dry etching is used. This is the etching process picture. Here, how the etching is done. First, we have first picture is shown the wafer, oxide film, and photoresist. And after etching, we have removed the unwanted material of the oxide and the photoresist. We have removed the unwanted material by just using the etching method. This is the picture of just how the overall the picture, just the semiconductor process, how the deposition, photoresist, exposure, development, etching, and photoresist removal is shown in this figure. The next we are going to see about the doping or ion implantation. Ion implantation this doping is nothing but introduce impurities into silicon to control electrical properties. The doping is adding impurities. The name doping called adding impurities. So here doping introduces impurities in the silicon to control electrical properties. The common dopants are boron, phosphorus, and arsenic. Here it is used by high energy ions implanted into wafer, and it is used. It is followed by annealing to repair crystal structure. And doping is the process of intentionally introducing impurities in the silicon to modify its electrical properties. This is essential for creating p-type and n-type regions in semiconductor devices. And common dopants we have seen as boron for p-type and phosphorus and arsenic for n-type. In boron we have the creator creates holes. In phosphorus or arsenic we have for n-type we have add electrons only for the electrons. The next one we have seen about ion implantation process. In ion implantation, high energy ions of the dopant element are accelerated and physically implanted into the silicon wafer. And after the ion implantation, the next main implantation is annealing step. Here the wafer undergoes annealing, which heats the wafer to repair damage to the silicon crystal lattice caused by the high energy. The annealing is nothing but repair. You are going to repair the particular silicon crystal lattice which is having the damage. Here, thus going to what are the damage caused by the crystal lattice, which is caused by the high energy ions and activate the dopants with precise control over dopant concentration at the placement. The next, the process enables precise control over the electrical characteristics of transistors and the other semiconductor devices, forming the foundation of modern integrated circuits. This annealing is the important process for the precise control. The next, we are going to see about the deposition techniques. Here, these are some of the deposition techniques: physical vapor deposition, chemical vapor deposition, and atomic layer deposition. In physical vapor deposition, it will be metal deposition, Al and Cu, and there is aluminium. Here the next one, chemical vapor deposition, oxide and nitrate layers, and as ALD, automatic layer deposition, very thin uniform layers for advanced nodes below 10 nanometer. And we are just before enter into the types, we are going to discuss about the deposition. What is the deposition process? Deposition process are used to add thin layers of materials onto the wafer surface, forming conductive, insulating or productive layers are required for the integrated circuits. The next we are going to discuss about the types of the deposition. The first one is physical vapor deposition. This PVD is primarily used to deposit metal such as aluminum and copper into the wafer. The process involves vaporizing the metal and allowing it to condense on the wafer surface, creating a thin conductive layer that is called as PVD. And next in CVD, here you have to deposit insulating layers of silicon dioxide and silicon nitrate in this process. In just you are going to have the gaseous precursor react chemically on the wafer surface to form a solid layer. And this chemical vapor deposition provides good step coverage and is widely used for interlayer dielectrics. The last step is atomic layer deposition. It is used to allow the deposition of ultra thin, highly uniform layers, often only a few nanometer thick. It is especially important for advanced technology nodes below 10 nanometer, ensuring precise control of film thickness and conformality even on a complex 3D structures. And together all these deposition techniques are going to enable the formation of conductive path, insulating barriers and gate structures in a modern semiconductor device. These three deposition techniques are being used for the formation of conductive paths and insulating barriers. And this is the picture of chemical deposition techniques. The next we are going to see about chemical mechanical planarization. Before entering into the types, we are going to see about what is chemical mechanical planarization. And this is in semiconductor manufacturing. The chemical mechanical planarization is used to smooth and flatten the wafer surface. It is essential for ensuring accurate patterning in subsequent layers. So, this chemical, this CMP is nothing but it is used to smooth or flattens the wafer surface. And it is used to planarize wafer for next processing layers and uses slurry or polishing pad. For example, used after copper deposition in a multi-level interconnects. And the process details are here the CMP, that is chemical mechanical planarization, is nothing but the combination of chemical reactions with the mechanical policy. Here you are going to contain a slurry abrasive particle and chemicals applied on the wafer surface, which is then polished using a specialized pad, and it removes the surface irregularity and creates a planar surface. Just it is used to smooth and flatten the wafer surface. That is called a CMP. And the main purpose of this planarization is in multi-layer semiconductor devices will be used. Without a flat surface, lithography or deposition later steps could lead to defect and misalignment. So, for the photolithography or deposition steps, without this CMP, it may lead to some defects and misalignment. For example, for instance, after copper is deposited to form a multi-level interconnect, CMP is used to planarize the copper and dielectric layers. This ensures each subsequent layers is uniform and reliable. And CMP is this chemical and mechanical planarization is the key to achieving the precision and reliability required for modern integrated circuits, especially as device complexity increases. This is the just picture for this chemical mechanical planarization, and using this polishing, but after the smoothing, and the main aim of the CMP chemical and mechanical planarization is you are going to have the slurry with the help of the polishing pad and polishing pattern. This is the picture of CMP, this chemical mechanical planarization. The next we are going to see about the transistor formation. Transistor formation is the core of semiconductor device manufacturing. There is metal oxide semiconductor field effect transistor form the building blocks of all modern integrated circuits. And here the first one is step of the transistor formation is gate stack formation. The process begins with the formation of the gate stack, which includes gate dielectric, that is called as insulators, and gate electrode. This controls the flow of current between source and the drain. The first step of transistor formation is gate stack formation. The next we are going to see about the second step, source drain implantation. Here, the source and drain regions are created through ion implantation, introducing dopants to define N-type or P-type regions that allow current conduction when the transistor is active. When the transistor is active, the current flow of current conduction is to happen through source or drain implantation. The third one is spacer formation. Here spaces are added around the gate to precisely define the junction depth and reduce parasitic capacitance, improving transistor performance. And the fourth step is high K metal gate deposition. In advanced nodes, high K dielectric materials and metal gates are deposited to reduce leakage current and allow continued transistor scaling. The next we are going to see the modern transistor structures for cutting edge nodes. Now we are using the FinFETs or gate all-around structures are used in the advanced semiconductor manufacturing devices. These 3D transistor architecture offer better control over channel current, lower power consumption and improved performance at extremely small technology nodes. And this transistor formation combines multiple precision processes to build the fundamental switches that powers CPUs, GPUs and other semiconductor devices. This is the transistor formation picture. Next we are going to see about metallization interconnects, and it is nothing but we are going to form the wiring that connects millions of or even billions of transistors on chip. Metallization interconnects is nothing but you are going to connect the transistors in the chip, that is called as wiring, allowing them to communicate and function together as a complete integrated circuits. The material used for metallization and interconnects are copper, tungsten and cobalt, and will be either the material will be chosen for their external electrical connectivity and reliability. The process overview this is the process for the metallization and interconnect. Here the first one is damascene process, where trenches and vias are etched into the dielectric, then filled with metal. Deposition technique is PVD, there is deposition techniques PVD or CVD, chemical vapor deposition, are used, followed by CMD, that is chemical mechanical planarization, to planarize the layers. Next we are going to see multiple metal layers. Here modern chips can have 15 to 20 stacked metal layers to form a complex interconnect networks. Each layer is carefully aligned to ensure accurate connection between transistors. For example, for high performance processors, CPU and GPUs use the multi-layer interconnects to achieve high speed signal transmission while maintaining energy efficiency. Metallization interconnects are critical in chip performance, as the speed and reliability of processor heavily depend on how efficiently these layers are designed and fabricated. For the performance or the speed of the CPU or CPUs, this metallization and interconnects are very essential. And this is how the chip transistors are made using built using the interconnects and metallization. Next we are moving on to wafer testing, and this the wafer testing is nothing but just essential quality control step in semiconductor manufacturing. It evaluates the electrical functionality of each chip while it is still part of the wafer. A stepping method used, chips are tested using probe cards which have tiny needles that make contact with each die pads. Various electrical tests are performed to check for defects such as open circuits, shorts or performance deviation. The wafer testing method is an essential one. The main purpose for the wafer testing is to identify defective chip early in the process, just to identify the chips which are defective, and it will be just control the damage which will be caused in this packaging side. So at the just previously when we are having the wafer testing, the identification of defective chips in this earlier is very just better, gives very better packaging for the semiconductor devices. This prevents costly packaging of non-functional device, ensures only good dies move forward. For example, for memory chips, wafer testing can detect faulty cells. Many designs include redundancy cells, allowing defective areas to be bypassed, effectively repairing the chip and increasing yield. Wafer testing is a critical step that ensures reliability, maximizes yield and saves time and the resource in semiconductor manufacturing. And this is some of the wafer testing, how just the picture shows the needle-like structure, and with the help of this the needle you can have in the wafer testing process. The next step is packaging process, and this packaging process is used to protect the chips and provide connection. And what is packaging is nothing but the process of enclosing the semiconductor die to protect it from physical damage, contamination and environmental stress, while also providing electrical connection to the outside world. So packaging is an essential one. And here the packaging types are the QF and BGA. Advanced packaging type are 3D packaging, chiplets, TSP, And the example is AMD Ryzen use chiplet based architecture, and the applications are improve power efficiency and performance in CPUs and GPUs. And packaging is the process just we are going to product enclosing semiconductor die into product from the physical damage or contamination or environment risk. The packaging type, just now we are going to see about the common packaging types, that is called DIP, dual inline package, older through hole technology, QFN, that is quad flat no lead technology. The next one, the compact surface, there is a compact surface mount package. The next one is BGA ball grid array, uses solder balls for higher pin density and better thermal performance. For the advanced packaging, the modern high performance chips, advanced packaging techniques like 3D packaging are used. In 3D packaging, stack multiple dies vertically, and chiplets multiple smaller dies combined in a single package to improve yield and scalability. Through silicon vias, electrical connections, enabling dense 3D and integration. And the example of this AMD is utilize chiplet based architecture, combining multiple dies into a single package to enhance performance and power efficiency. And the applications are advanced packaging improves overall power efficiency, speed and integration density of CPUs, GPUs and other high performance devices, making it critical for modern computing systems. This is the semiconductor packaging. Just from the wafer you are going to give as a single chip. This is also called as die, then it is called as packaged semiconductor devices. And this is the overall semiconductor manufacturing process from the sand, that is quartz sand. From the quartz sand, just we can form the silicon. From the silicon we have the formation of wafer. From the wafer we have the several steps to form as a semiconductor chip. And the next one is final testing. After the wafer testing, we are moving into the final testing. The final testing is having the different types. There is functional testing, burn-in testing, reliability testing, and only passed chips are shipped. After the testings, this passed chips only shipped. Before the testing will be in a failed manner, we have eradicated the chip and we are moving to the next testing. And the example of this testing, automatic chips undergo extreme temperature and cycling. And what is testing? Final testing is the last step before semiconductor chips are shipped to the customer. It ensures that only fully functional reliable devices reach the market. And the functional testing, we are having the different testings are there. In the functional testing, each chip undergoes through functional testing to verify that it performs all implemented operations correctly under normal operating conditions. But in burn and in testing, it will elevate temperature and voltage for a period of time to detect early life failures. First, we are going to have the chips to a elevated temperature. We show the chips to the elevated temperature. When the temperature is high, if the chip is having any detect or something failure is there, it will show the failure at the early time. So, if you want to detect the early life failures, we can have the burn-in test. This helps ensure long-term reliability. The next one is reliability testing. Here, the reliability test simulates extreme environmental conditions such as temperature, cycling, voltage, stress, and humidity to ensure the chip can withstand real-world operating scenarios for the reliability testing. The passing chips, only chips that pass all the tests are packaged and shipped, reducing the risk of failure in critical application. Here, the examples are automatic chips, for instance, undergo rigorous temperature cycling and vibration tests because they must operate reliably under harsh conditions. And final testing and reliability verification are crucial for maintaining customer trust, performance, device longevity, especially in high reliability sectors like automotive, aerospace, and medical electronics. And next, we are going to see about the applications of semiconductors. And applications are consumer electronics, the smartphones, laptops, and CVs, industry and automotive, EV power management, sensor, motor, and drives. And in medical we are using MRI processors and diagnostic system. And in aerospace, just navigation and control system. And the real-time example we are having in real life, Tesla uses advanced power semiconductors, IGBTs and SiC MOSFETs. And here the Tesla have the advanced power semiconductors. IGBT is nothing but insulated gate bipolar transistor, and the SI is just silicon carbide MOSFETs. These components are just having the high efficiency inverters and converters into the electrical powertrain. These are some of the applications of semiconductor. Next, we are going to see about the challenges. What are the challenges we are facing for the manufacturing of semiconductors? We are going to discuss now. These are some of the technological and physical hurdles we are facing in while we are having the manufacturing process. The first one is miniaturing and scaling. Shrinking transistor to atomic level reduce quantum effects, demanding constant innovation in photolithography and materials. The first one is miniaturing and scaling. The second one is thermal management. And in packed transistor, when dense packed transistors generate immense heat, require new material like SiC and just GaN, and designers for a heat dissipation. Gallium nitride for a silicon, we have having the heat dissipation. The thermal management is there. The next one, contamination control. Even microscopic particles can ruin chips, requiring extreme clean room standards and purity levels. The contamination control will be an essential one. This main challenges. The process of complexity. Process complexity in multi-stage process fabrication, testing, assembly involves intricate steps like delicate chip packaging and precise etching. How to overcome them? Here, how to overcome the challenges we have faced in the time of manufacturing semiconductor. The first one is artificial intelligence and machine learning. Here, you are going to analyze the real-time data to optimize process parameters, predict failures, and enhance yield with smart manufacturing. And the next one is advanced lithography. Use multi-patterning and extreme ultraviolet UV lithography to create smaller features. What is multi-patterning? We have multi-patterning in the photolithography process. We have the multi-patterning techniques we are going to use. Next, material innovations are develop new materials to overcome physical limits and enable advanced device structures. And the next, 3D integration wafer level packaging. Integrate components vertically to improve the performance and reduce footprint. The next, smart manufacturing industry 4 point, we can implement the smart manufacturing. And the next one is supply chain diversification. By build regional ecosystem and diversity suppliers to reduce the reliance on single forces. Workforce training, invest in education, apprenticeships and specialized programs to bridge the skill gap. Sustainable practice, develop greener processes, improve chemical recycling and reduce energy or water consumption. And what are the future trends in semiconductor manufacturing? Here, this is the future trends in semiconductor manufacturing. Already Taiwan and US, Taiwan manufacturing semiconductor, and in US NVIDIA and Samsung and South Korea. These are the companies which are having the trends as up to 2 nanometers. And in India, it is till now we have not completed 10 to 2 nanometer beyond nodes. So future trends in semiconductor manufacturing are 2 nanometer and beyond nodes. UUV, that is extreme exposure ultraviolet high nano lithography, numerical aperture lithography, 3D stacked chip architectures, graphite transistors, quantum and neuromorphic chips, AI-assisted manufacturing. So these are the future trends, and these future trends are used to evolve rapidly, driven by the demand for higher performance, lower power consumption, and more compact devices. And 2 nanometer and beyond nodes, chip makers are pushing beyond the 3 nanometer, 2 nanometer, or even smaller, enabling more transistor per unit area, which translates to higher processing power and energy efficiency. UUV high numerical aperture lithography is an extreme ultraviolet lithography with the high numerical aperture tools, allows finer patterning at these advanced nodes, critical for scaling down features while maintaining accuracy. The next one is 3D stacked chip architecture, and it allows multiple dies to be vertical. The dies is nothing but we are calling the single chip, semiconductor chip as dies to be vertically integrated, improving performance, reducing footprint, and enabling faster interconnects between the layer. Next, in the graphite is gate-all-around FETs. Here it is the next generation transistor architecture, offering better channel control, lower leakage, and high efficiency than traditional FinFETs. Nowadays we are using the FinFETs, and now the future trend we having the gate gate all around FETs. This is used for a lower leakage and channel control. The graphite transistors are used. The next one is quantum and neuromorphic chips. Emerging chips designs like quantum processors and neuromorphic chips open new horizons for computing, enabling tasks like quantum solution and brain displayed AI processing. The next one, AI assisted manufacturing systems. Here, with the help of the AI, which is rapidly increasing, being applied to the semiconductor manufacture for predictive maintenance, yield optimization, and process control, making fabrication more efficient and reliable. And these trends in the semiconductor industry is moving forward to smaller, smarter, and more energy efficient devices, laying the foundation for the next generation technology from AI to quantum computing. Next, we are going to discuss about what are semiconductor manufacturing companies all around the world. The major semiconductor manufacturing companies and their specialties we are going to discuss now. The main all around the world, the Taiwan Semiconductor Manufacturing Company is the just is holding the 60 to 70% of shares in the semiconductor manufacturing companies, and the headquarters in Taiwan. It is main specialty are pure play foundry, advanced nodes up to 5 nanometer, 3 nanometer, and 2 nanometer roadmap. Notable clients are Apple, NVIDIA, and AMD. And the main strengths of this Taiwan semiconductor manufacturing companies are leading edge UV lithography, high volume production, and strong R&D. And the next one is world all over the world. The next major famous company is for the semiconductor manufacturing is Intel Corporation. The headquarters in USA, integrated device manufacturing, CPUs, GPUs, and FPGAs. Advanced technologies like 10 nm and 7 nm nodes are used, and the advanced technology as gate all around the FED research is be used in Intel Corporation. The main strengths are vertical integration, design test fabrication, in-house chip architecture. And the third one is Samsung Electronics, the headquarters South Korea. Here the memory chips are the main specialty of the Samsung is memory chip manufacturing, RAM and NAND, foundry services, logic chips. The advanced technology used in Samsung Electronics are 3 nanometer graphite and UV lithography. The main strength is memory leadership, large scale foundry capacity. And the next is global industry. The headquarters is USA. Here the main specialties are foundry services, 12 nanometer to 14 nanometer mature nodes. Strength is the specialty process technology, automotives, and industrial chips. The next, Micron Technology, the headquarters is USA. Here the main specialty of this Micron Technology is the manufacturing of memory chips. The main strengths of this Micron Technology is high performance memory solution, AI and automotive memory applications. The next one is SX Hynix. This is the headquarters of SX Hynix in South Korea. It is also used used as the specialty of in manufacturing as memory chips, DRAM, NAND, and storage solution. The main strength is the high volume memory production, technology for AI and data centers. The next is Texas Instruments USA, specialty in analog and embedded processors. Industrial this major strength is industrial electronics, automotive chips, mature process nodes. The next one, all semiconductor Infineon Technologies, headquarters is USA or Germany. The main specialty is power semiconductors, automotive sensor. The strength of this company is automotive electronics, energy efficient power devices. And the next we are going to see about the semiconductor manufacturing companies in India. In India, for wafer fabrication and manufacturing, only we have the Tata Electronics. Here it is located in Gujarat. So focused on memory chip assembly and test. The Tata Electronics and Micron Technology just both will be the wafer fabrication and manufacturing. Both the companies are located in Gujarat. The next, Baidana Semiconductors. Here it is also used in Gujarat. And the main role is process and the device equipment facilities engineers are with there. So main we are having not the manufacturing of semiconductor. Here also we are having the manufacturing of small memory chips. Small memory chips are here. And next one is IMS India Semiconductor Machine Corporation. Here it is located in Karnataka. Plant fabrication in Karnataka, but it is moved on now. It is not just plan is cancelled and it is moved on to. We are going to see about the ANTP assembly test and mark package. For the assembly test and market packaging, the main company we are using KNS Semiconductor. Here packaging or test engineer, production engineer roles are in the KNS Semiconductor. The next one is CG Power and Industrial Solution OSAT. For the manufacturing and the quality checking will be done in, it is located in Gujarat. Next one is SPL Semiconductor, roles test engineer and processing are done in this SPL Semiconductor, will be located in Tamil Nadu. And next we are going to see about what are the opportunities for EC and triple graduates. What are the opportunities we are having in the semiconductor process? For next 10 to 15 years, the semiconductor will be in a high booming side. So, what are the core areas we have chosen to study for the semiconductor manufacturing process? This VLSI design, chip verification, physical design, analog, mixed signal, embedded system testing, fabrication, process engineering. These are the core areas. The main key roles are they are need of VLSI engineer, test engineer, process engineer, layout engineer, embedded system developer, RF engineer. Just in the upcoming 10 to 15 years, these are the main key roles which is will be needed in semiconductor companies. And the companies hiring in India are Intel, Qualcomm, AMD, Micron, Samsung, Apple, alongside domestic players and startups are in urge of hiring the semiconductor known workforce for semiconductor manufacturing. And how we have to succeed in the semiconductor manufacturing? What are the basic fundamentals we have to know is master digital logic, circuit theory, and CMOS fundamentals. Next, in the industry, we have to have the gain proficiency in Verilog system and EDA tools using Xilinx or Cadence. We have studied the Xilinx or Cadence software to learn the industry's tool. Next, if you want to have the knowledge about EDA or RTL design or VLSI concept, will be better choice to succeed. The next one, practical experience, hands-on project in chip design are essential to bridge the gap between academics and industries. And coming to the last side, before concluding the semiconductor manufacturing device process and what are challenge we have facing, and the semiconductor manufacturing is the booming in the idea of India national semiconductor mission. For the upcoming 10 to 15 years, the manufacturing of semiconductor will plays a major role in our India market. So, our India having the mission to implement Make in India, this Atmanirbhar Bharat, to introduce the semiconductor manufacturing. And with this, in relation with this semiconductor manufacturing, for the electronics and communication students, there are a lot of job opportunity available for the electronic communication students. And thank you.